does this look like the first derivative to you?
Of the one that we did of 3?
Yeah.
Yeah.
Yeah, that does look great. Okay, so now the second derivative here is this is product rule and this is product rule, so it's kind of a hassle. You could use the this form where we had left it like this. You could do it like this, where this and this are products. That's probably easier. UV.
Okay.
So let's do that. So it's e to the 1 over x squared, and then the derivative of the inside function over here is 2, and then derivative of 2 over x. This one's probably the most maybe unclear one, but it's negative 2 over x squared is what this becomes. The 2 over x, so it becomes plus because there's 2 negatives, 2 over x squared plus, okay, 2x minus 2 over x, and then the derivative of this e to the 1 over x squared. And if you look back, you'll see that the derivative of 1 over x squared is negative 2 over x cubed. All right, so not great, but these both have this 1 over e to the 1 over x squared in them, so you can factor that out. And then what do we have left over? So we have big bracket here, 2 plus 2 over x squared plus, now you have to multiply minus 2 over x cubed by each of these, so that's minus 4. One of those x's cancels over x squared.
Okay.
And then minus 2 over x times that is plus 4 over x to the 4th, like that.
Why did it cancel in the 2x and it added in the?
Because this is on the top. This is the numerator.
Yeah.
And this is in the denominator.
Oh, I see. It cross canceled. Okay.
Okay. So then you have the following of e to the 1 over x squared, 2 minus 2 over x squared plus 4 over x to the 4th. Okay, and this you have to set equal to 0. So the more calculus you take, the more like they actually expect you to do stuff like this, which would be really hard, like algebra 2 pre-calculus problem. So the first thing is that x cannot be 0. We already know that because of this, and so you can because you're setting this equal to 0, you can actually multiply everything by the x to the 4th.
Okay.
So you multiply everything top by x to the 4th up top to clear it out here. So you get 2x to the 4th minus 2x squared plus 4. And then you can actually factor 2 out. So you get x to the 4th minus x squared.
Wouldn't the x squared cancel out because it's x, like?
It does. This x to the 4th goes with all 3 though.
Right. So then what happened to the x squared on the bottom?
It's x to the 4th up top over x squared.
Oh, I see. And then that turns, okay, gotcha.
Right. So then this actually factors, believe it or not. Okay. So is no, I made a sign error. Uh-oh. This was supposed to factor. Uh-oh. Yeah. This is bad because it doesn't work like this, but I made a sign error because this does work if it's plus minus, which is what it's supposed to be. Sorry, that's why I didn't want to do these. These get really bad here. Let me just double check. No, that actually is right.
So it doesn't factor.
Yeah, it does. So it's horrible here. It's x. You can use quadratic formula. X squared plus 2. Is it plus 2?
Oh, in the original function?
No, down here it is. It's +2. Actually, this never. Oh, that's good news. This never equals 0. So we caught a breaker. This is actually correct. I was thinking something else would be correct. So this never equals 0.
Okay.
And you use quadratic formula on that. So since it never equals 0, you have sort of the same problem that you had in the first derivative, where since x cannot equal 1, when you do your sign chart, the break point is at 0. So you have to test a point there and there, like -1 and 1, and you test it. You test it back in like this line here.
Mm-hmm.
So let's just try 1. So 1 is over here on the left. The e to the 1 over x squared is always positive. So it's 2 minus 2 over 1. So that's 0 plus 4. So that's positive. Okay. So this one is always positive. And the -1, this e to the 1 over x squared is always.
Can you not test it in the simplified version, the 2?
It would not, you can, but if you made a mistake here, it would propagate through the whole problem. So it's better to go back to the rough one. Although this does work. I mean, I need this e to the 1 over x squared here, but yeah, I mean, it does work. So let's do it in here. You'll see it's the same. So -1 is 1 because it's positive,
Yeah.
-1 positive. So that's positive as well. So you get 1.
E to the 1 over -1 is positive.
E is always positive. E
Okay.
to anything is always greater than 0.
Okay.
So this thing is concave up everywhere. Like when we get back to the actual question.
Wait, a -1 is positive, right?
Yes, positive. Let me just look at a quick graph of this. Yeah, it is concave up everywhere. So the graph of this thing, which I think it looks like this, and then another looks like that, and that's always concave up.
So would you write negative infinity to positive infinity?
Nope, you got to exclude 0 because it's not defined. It's not defined at 0. Yeah. And if it was multiple choice, you would see that answer.
And then never concave down.
Never concave down.
Okay.
All right. So now 13, we can look at 13.
It says find any local extreme values and inflection points.
Oh, really? Okay. So there's no IPs because there's no place where it switched from positive to negative or negative to positive.
Uh-huh.
So if we go back to our derivative, that's where we can figure out when we set this equal to 0, we made a sign chart. I remember we had -1, 0, and 1. You remember doing that from yesterday?
Yeah.
Okay. Do you have the signs handy?
From yesterday?
Yeah. If you don't, I'll look as well. Get them up here.
It was negative, positive, negative, positive.
Okay. So this one doesn't count right here because it's undefined, but you can see that this is a min and this is a min as well.
So wouldn't -1 and wouldn't -1 and 1 both be inflection points in that case?
The inflection points come from the second derivative.
Oh, okay.
And if you look at the graph here, which I know you wouldn't have, that confirms it. You know, that's -1 and that's 1.
So inflection points are where they're across the x-axis, right?
Actually, no, inflection points are when the second derivative changes sign.
Oh.
And the second derivative doesn't change sign anywhere.
So then do extreme values come from
the first derivative? Okay. Yes, first derivative.
And there aren't.
There's a min. There's 2 mins, 2 relative mins.
What about zero? Oh, but zero is excluded.
Yeah, it's excluded. It's an asymptote in the original graph.
Gotcha. Okay.
There's a lot going on. You're doing well to keep up. It's not that easy to do.
That was a hard one.
Yeah, a lot there. Usually you get a polynomial to do this kind of analysis. Okay, 13 has like the same set of things that it wants. Just I don't know why they didn't just make it 3 through 16. So like it's kind of like two problems. It's like you do everything for this e to the minus x, but you only look at it for less than 0, and then you do everything for this 4x minus x cubed, but you only look at it from x greater than 0. So let's just do them kind of down, side by side here. Okay. So let's take the derivative of each. What is the derivative of this one on the left?
It's
e, so it's
stays the same.
Okay, and then here you've got chain rule. So what's the derivative of the inside function? Derivative of negative x?
Isn't it just 1?
-1?
Yeah, -1.
Okay, good. Now over here, this is power rule.
So, okay. 4x.
The x goes away because it's only one here.
Oh, well, I keep the first, and then I was gonna do the.
This is product. No power. No product. This is not product.
Power rule.
Power rule. They sound the same when you're thinking about these.
4 minus 3x squared.
Great. Okay, so you set this equal to 0, and I mentioned before e is not equal to 0 anywhere. So this contributes nothing.
Yeah.
This does not, but this does. This you can set equal to 0. So you have 4 equals 3x squared. You divide both sides by 3. Take a square root of both sides, it's plus or minus. So you have x is plus or minus square root of 4/3. But this one is only good for x greater than 0. So you exclude the negative. You exclude negative square root 4/3.
Okay.
And I think that's why this is here, because it's like, oh, you got to make sure you forget that. They don't forget to exclude it. So now when you make your sign,
it's out of the domain. That's right.
Yeah. So now when you make your sign chart, what's kind of interesting here is that you do have to do it from -infinity to infinity. Okay, but and you have this sort of this break point here at 0, but it's not really it's not an undefined place, but you do need to like pay attention, like this one's you're only focusing on the one on the left over here, and then over here on the right. So it kind of is, I don't really know what to put here, but if we test a point over here, the e is always negative. Okay, and then over here, our one critical point is at positive square root 4/3. So you have to test something between 0 and square root of 4/3. So be really careful about like what you choose there, because you could choose something that isn't quite right, like meaning too big. It's the square root of 4/3 is 2 over the square root of 3. And if you multiply top and bottom by 3, it's 2 square root 3 over 3. And I don't know if that helps at all. Are you allowed to use a calculator on this part?
I don't know if this would be in the calculator part or not.
Yeah, and that's kind of a rough one to figure out, because it's actually really close to 1 when you end up doing this. So let's just pick like be safe here. Let's go like 1/8 as our test point, right? It's not great, but like, okay, so 1/8 squared is like 1 over 64, 3 over 64, so it's probably positive.
Yeah.
Okay, it's like we can do that. Now you might think from minus to plus is something here, but it's not, because it switches, like they're two different functions. Like the original, it's a break between the two graphs. Maybe
like they're two separate graphs, like they're two.
Yes, like they don't necessarily connect at 0. I know you can't do this on the exam, but let me show you the graph, because I think it would be helpful for this one. And your instructor's being quite difficult here giving you this, because it's just tough. If you don't have the graph, there's so much you can do with the graph. Okay, and then what did we say here? 4x minus x cubed for x greater than 0. Let me zoom in here. Snip this in. All right, so let me give you, so here's what the graph looks like. And you can see they're not connected,
I see.
but this is decreasing. That's consistent with what we have here. And this little part is increasing. That's what we have here. And then you can see since it's going down, if we were to test a point over here, if we tested like 5, something really far away from that to make sure. If we tested 5, it's 4 minus 3 times 5 squared. Yeah, it's clearly negative there.
Okay.
Is that okay? Is that clear?
Yeah.
So that takes care of the first part. So now we have to figure out where is it increasing. It's increasing wherever it's positive. So from 0 to root 4/3. And it's decreasing everywhere else. It's decreasing from
negative infinity to 0.
Yep.
Yeah. 4/3 to infinity.
To infinity. Very good. Now we can do the local extreme values right now. This minus to plus is nothing, and it's confirmed by the graph. But this plus to minus is something. What is this point? It's a max. We see that in the graph there. So this is part A, B, and so you actually do E before the next. So E is a max at x equals root 4/3.
Do you when they ask for the local extreme values, you don't need to find like the y or anything, right? You just give them the x coordinate.
It's unclear. Sometimes it says it wants both. It wants the x and the y.
Okay. I think he said that he just wants the x, if I remember.
In this one, it's a lot of work because you got to go back in, you got to square it, you got to put in the e. Like it's not, and even like I said, that this is the right answer, not the root 4/3. This is the simplified version of it. But they tend to be less interested in that in this class.
Okay.
Okay, so now we got to find y double prime, but we got to do it for both. We got to go back here to this line. Let me grab all of this, and we'll just show the progression here of it, and that way you got some context here. So you found your first derivative, hooray! And then now you got to find your second derivative. So on the left here, it's still just e to the minus x, but there's a negative out in front. So it's itself times -1. So it ends up just being e to the minus x.
Oh,
what? I'm sorry.
No, I said e to the x, but it's e to the minus. Okay.
Yes. And then y double prime here, the derivative of 4 is 0.
So
this is minus 6x. Yeah.
Yeah.
And that equals 0 when x equals 0, but that's not very helpful because again, on your derivative line, it's not a break in the domain. It's just that it's where they split at 0. So this one is nothing.
How do you know that they're two separate when you're just looking, like if you don't have a graph?
Because they're piecewise. Maybe I didn't.
Oh, I got you. Okay.
And that's strictly because it's a piecewise problem.
Got you. Okay.
Again, kind of unusual to get that on a test that I've seen over time, but I don't know. So then you're looking over here to the right of 0, and you're like, where's my critical point? Well, or possible inflection point? Well, it's here at 0, but 0 is right there, so it's nothing. Like if it falls on that point, it's no good. You're looking for something over here to the right. So again, you got to test something. So let's say you test, -1. E is always positive. It was negative in the last one because there was a negative out in front. Minus 6x. If you put a positive number in here, like 2, this is negative, but this is not an inflection point. No inflection point here. And I know it goes from plus to minus, but it's not part of the domain's undefined there, so you can't use it as a breaking position.
Okay.
And again, if we go back to the graph, like there's no inflection point. Like that's not an inflection point. Although it's kind of interesting, it does go from concave up to concave down there. But it's not continuous either. So that's part of the problem for this.
So it's concave up from, can you go down a little?
Sure. So to answer part C, I know you need the answers. Sorry for not being more clear.
No. So it's negative infinity to 0, right?
Yes.
Okay. And then down would be 0 to infinity?
Yes.
Okay.
All right. 3, 13, 17. We did 17. We did 23, 36. 36 would be our next one.
Yeah.
Right. 36. Connecting F prime. Okay, so part C is a graph. You said we're not doing any graphing in this test. Is that?
Just no like sketching, yeah.
Okay. All right. All right, find the absolute extrema of F and where they occur. So absolute extrema are kind of different than relative extrema. Like relative extrema, you just look at the derivative where it changes sign. So like, do you see how F prime changes sign here from minus to plus?
Yeah.
Okay, so there's something going on there, and that looks like it's a min at 1. It's a min at 1. So, but if we go to 1, the output there is -2. So probably it's both a relative min and an absolute min.
What's the difference between the two?
Okay, so let me draw a picture where I think it'll have all of this in there here. So here is, this is the absolute min. Here's a relative min, relative max, a relative min, and then an absolute max. So this is a relative max, relative min, absolute max, I'm sorry, min, absolute max. But there's other graphs where like the relative min and the absolute min could be the same. But this is like the relatives are where the derivatives are equal to 0. The absolute maxes are either the endpoints or where the derivatives are equal to 0.
Okay.
Yeah, it's not clear. I know it's not clear. Yeah, this is not a good problem for you trying to learn this, but you know, if you just look at this line right here, you know from your sign chart, from all the stuff we've done, that if it goes from minus to plus, that's a min.
Yeah.
Now the question is it an absolute min? So look at this row right here. Do you see any F values smaller than that?
Smaller than what?
-2.
No.
So it's both. Like it's the relative min, but then you look to see maybe it's an absolute min. It's an absolute min if it's smaller than everything else.
So if there was like a -3 on there, it would be a relative min, but not an absolute min.
Yes, you said that perfectly.
Okay. So it's like absolutely the minimum. I see.
Yes. Now for the max, there's no relative max because it's plus plus. And so nothing's going on there. So then you're just looking at what's the biggest value in here.
3.
So that's the absolute max.
It's also is it also the relative max?
Oh no, only if there was a sign change here. Yeah.
Okay, got it.
Okay. Yeah, that's part A.
So then the inflection point would also be, wouldn't that be -2 as well?
You're looking at wherever the second derivative changes sign.
Second, right?
Yes.
So never, there's no inflection point.
There's no inflection point.
Okay.
Did we do the right one?
36, right?
Oh yeah. Okay. I'm sorry. It was like didn't look right. Okay, 39.
Wait, so for if you would, I could just use Desmos actually to graph it.
We're talking about 39 or something else.
For 36.
You can't graph anything here because I mean, you could plot some points, I suppose,
Okay.
if you wanted, like 0, 0 is there, 1, -2 is there, 2, 0 is there, and then 3, 3 is there. So see how the curve looks like that? That's why this is both the relative min and the absolute min, but this is the max because it's the highest point.
Gotcha. Okay.
Okay, can we move to 39 or do more
Yeah.
questions on this? Okay, 39.
Oh yeah, I'm really confused with linearization. So if we could spend some time on that.
Sure. This is probably not the best problem to do to start with, but we can do this first if you would like. I can provide an easier one if you think that would help.
Yeah, let's maybe start with an easier one and then.
Okay, so we're gonna start with y equals x squared. You're gonna tell me the derivative is 2x, and we want the linearization at 1. We want this at x equals 1. So essentially, this whole linearization is tangent line. Is finding the tangent line. So let me do a quick graph here of this so you can see visually what's happening. 2 times. Okay, so let me get this. I'm gonna snip it in. All right, so here we go. Here's a picture. So what you are doing when you're doing linearization is your original function is this red one. And I said we wanted the linearization at 1. You're finding this line at 1 that goes through this point, and then you could use it to approximate other points along the line if you needed to. Okay, and do you see how like it's a pretty good approximation, like near 1?
Yeah.
But like over here at 0, it's not so good, and at like -1, it's terrible.
Yeah.
So that's why it's called a local linearization, because it's good near there, but it's not good
That point, right?
further away. So how do you find it? Well, you need the derivative. What does the derivative tell you? It tells you the slope. So when x is 1, what is the slope?
2.
2. So you know your slope is 2, and then you need a point.
You use the second. You use the first derivative for that though.
Yes. Yes.
Oh, okay.
And you need a point. So your point comes, okay, when x is 1, what does y equal? Y is 1 squared, so y is also equal to 1. So you need a point, 1, 1. So you need this point right here. So the linearization of x, okay, is f of this point A, so this is actually called A, plus f prime of A times x minus A. So we're going to fill those in, and you're going to see that this is just point slope form. So the linearization of x, f of A, what is f of 1? That's the y value, that's 1. Plus, what's the derivative at 1? The derivative at 1 is 2. A is 1, okay?
Okay.
So notice another way to write this, 2 times x minus 1 plus 1. And if I wrote point slope form below this, you would see that all I did was move this value over.
Okay.
So all you're doing, you're finding 2 things. You're finding the ordered pair, and then you're finding the derivative, and you're evaluating that at that point. So this is the formula you need. This thing.
Wait, so
right.
So do you need the wait, how did you get the y again?
From x.
Oh, you just plugged it. I see.
Yes, just plug it back in. So this is a very simple example. We're going to go back and do this one
Wait,
right here.
Wouldn't y be, if you plug 1 in, to the original?
To the original, yeah.
Got it. So then the linearization is that whole last line?
Yep. It's the tangent line.
So the 2x whatever.
Yes.
Okay.
Yes. Okay. So for this one, so for part A, forget all this other stuff. We're going to do this, but not right now. So in part A, okay, you need to find f of x. So f of 0 is -1. That's given. Like you don't have it, but they give it to you. So there's an ordered pair here, 0, -1, but you need that. The next thing you need is f prime of 0. Do you see how they give you a derivative already? The derivative is given.
Yeah.
So that's sine of 0 squared. Sine of 0 is, that's on the unit circle, that's over here, that's the y value right there.
Okay.
Okay, so as I mentioned before, the linearization of x is the following formula. It is f of a, your a in this case is 0, that's your a,
So
plus
that's
f prime of a times x minus a.
So it's 0 plus.
F of a is -1 though.
Oh, okay. -1 plus.
The derivative is 0.
Okay. Wait.
So,
So then.
so let me try to map these points. This point is here. This number is there. This x value is there. There's a lot of repetition here. Maybe that's why it's not repeated values, so it's not clear. But essentially, it just becomes -1.
Okay.
So we don't know what the graph looks like, but like at 0, it has a tangent line that's horizontal at -1.
Okay.
This is not a good example. But it's okay. All right, so the next thing is they want the approximate value at x equals 0.1. And this is going to be unclear maybe, but they're basically asking you to evaluate L of x. Let me snip this in. They want L of x at 0.1. And this is one of the things that I hope you remember, because it at all values of x, it's -1. Like L of 0.1 is -1. L of any number you want is -1 because it's always -1. Normally you'd put it into something for x, but it's not there in this one.
Well, where did you get the -1 from?
The previous line here. This is the linearization.
Oh, so the linearization of any number will be -1 is what you're saying?
For this particular thing that they're giving you, yes.
Okay.
But in the one that I gave you, see how the linearization is a line?
Yeah.
So let's say we wanted the linearization of 1.1 here in this one. You would put 1.1 in for x.
So why don't you do that for the other one?
Because there's no x, and it's that's why they said there's a bad problem, because it's.
Oh, because the linearization that we got is just a single number.
Yes, it's constant valued, so it's always the same.
Okay.
So it's not all that interesting. The next part is writing to learn. Oh, boy, can we skip that, or do you need it for?
I mean, I need to do it eventually, but
Okay, so we'll do it real quick then. So it has to do with the following situations. Okay, so let's say the graph is increasing and concave up, and your tangent line here that is a little bit further away, is this an overestimate or an underestimate?
over.
Over. So that's an overestimate. Let's say it's concave down and decreasing. That's an underestimate.
Yeah.
Okay, so the other possibilities are it's concave up. So that's actually, let me put that on the right here. So this is also an underestimate. And then there's, what am I missing here? This one. What am I missing?
Wouldn't that one be an under too if you drew a line?
Yes, but there's supposed to be 2 overs. So what did I do wrong? This is also an under. Oh, this is an over. Sorry, this is an overestimate. Okay, because the line's it's above that line.
Oh yeah.
So you need to know this, because what we need now is we need to know the sign of the first derivative. We need to know the sign of the first derivative at 0.1. And we need to know the sign of the second derivative at 0.1 because it'll tell us which of these four that it is. So let me go through that. F prime of x is sine of x squared. We need f prime of 0.1. Sine of 0.1 squared. Okay, on your unit circle again, that's over here in the first quadrant. Like 0.1 is somewhere in there, maybe roughly. So that's positive. So that tells us that it's increasing. So it's either, here's the possibility, it's either this graph or it's this graph. So now we got to find the second derivative to figure out the concavity. Because this is concave up. Go ahead.
Isn't the derivative, so you, oh, never mind. I see. They already
So
gave
one's up, one's, yeah, I thought they gave the original function. So now you got to find the second derivative. So this is a chain rule. Derivative sign is cosine. Keep the inside function times the derivative of the inside function, 2x.
Okay.
Okay, now you have to evaluate f prime of 0.1. So it's cosine of 0.1 squared times 2 times 0.1. Cosine is also in the first quadrant, it's positive. So we assume we're there roughly, probably okay. And then, so this is positive. So that means it's concave up and increasing. So it's this graph right here. It's not that one. And so our tangent line is an underestimate. Because
so it's less than the approximation?
Yes. No, I'm sorry. Let's is the actual value? Yes, it's no, the actual value is greater. This is f of x and this is L of x.
So which one was our actual value?
The actual value is up here. It's above. This is the original curve.
No, but like, did we find the actual value?
No, we don't need it. We just need to know whether it's concave up and increasing. So we did all this to figure out that the original curve is concave up and increasing. And
right.
that tells you this is the tangent line. So it hits, I got too many lines going. It hits right there. But the point we care about is right there. It's 0.1 away. So that the tangent line of the linear approximation is below the actual value.
Okay. Okay.
$40. dy, value dy, okay. So 39 and 40 are like one-offs that I don't know. I would ask my instructor, like, do you expect me to know this for the exam? Because you're only getting one of them.
Sure.
But I guess the same, because I think we only did one optimization and one related rate. So maybe it's fair here. Okay, so this says here's why, and I want you to find dy, and you might be thinking, well, like this doesn't look quite right. It's because it's not. You find your derivative and then you multiply it by dx. So you find dy using product rule here. X squared e to the minus x times -1 plus e to the minus x times 2x, but then you multiply it by dx.
Okay.
And that's this. It's a little bit different, but that's what it is. So you can clean this up a little bit inside here. There's an e to the x in both. So it's e to the minus. Go ahead.
You just got the, where did you get the -1 and the 2? Oh, that's just a product rule?
Product rule, yeah. Product rule.
Gotcha. And then the -1 is
from the derivative of the negative x.
Okay, because chain rule.
Yes.
Okay.
Okay, now the 2x I'm going to put first, and then this negative goes with x squared, so I'm going to write minus x squared.
Is there no chain rule for the x squared?
There is not.
Okay. I'm kind of confused when there is a chain rule or not.
Okay. let's finish this problem and then
Okay, sorry.
address that because we're really close here. So this is part A. Part A is done.
Okay.
Part B is to evaluate for x equals 1 and dx equals 0.01, which requires a calculator. E to the minus 1, 2 times 1 minus 1 squared times 0.01. Actually, it doesn't require a calculator. It just seems like it would. So 2 minus 1 is 1. So it's 1 over e times 0.01. 1.01 is 1 over 100. And this is 1 over e. So it's 1 over e times 1 over 100, which is 1 over 100 e.
Do you would you need to put that into the calculator, or would you just leave it like that?
This would be totally correct.
Okay. So when you have an e, you're not expected to multiply it out or anything.
Yes, that's done now. So yes, great question. Because this is the core like calculus thing. You have to be able to take a derivative of everything you see in this class. And if you're unsure when to use just a chain rule, we gotta get that clarified. So let's say it's sine of x squared.
So it's cosine of 2x.
Keep the inside function.
Oh, product. Oh, okay. So cosine 2x plus.
No, you keep the inside. You keep the inside as is, and then you multiply by 2x. This is the chain rule. This is not product rule because it's a function of something.
So what's the difference between that and a one that would need a product rule?
Well, we're gonna get there, but is this one okay?
Yeah, that makes sense.
Okay. So let's say y equals x plus 1 squared. Okay. And we'll compare that to y equals 4x cubed plus 1 squared. Okay. So the one on the left here is power rule. Do you see that?
Yeah.
2 times x plus 1, but it kind of is chain rule because what's the derivative of the inside function?
1.
So it is, but it isn't. Like you wouldn't include that in the answer. But over here, you for sure have a chain rule because it's 2 times keep the inside function, but then the derivative of the inside function isn't 1 anymore. It's 12x squared.
Yeah.
Okay. So now there's two possibilities for product rule. Like one is I tell you that it's like e to the x times cosine x. There's no chain rule in this.
So for the first example that you did, the sine, where was it?
Sine x squared.
But aren't those two things? So if it's like a sine of something, it's not product rule, right?
No.
Because it's not like two things being multiplied together.
That's right.
Okay.
Okay. Now, down here, this is product rule, but there's no chain rule.
So it's e to the x times negative sine x plus cosine x e to the x. Okay.
Right. But now let's make one kind of like it. Let's say it's y equals e to the x squared times cosine of, I don't know, x cubed. These now both have chain rule in them.
Okay, so, but it's still product rule.
It's still product rule. So
e x squared times negative sine of, times 3x squared.
Good.
Plus cosine of x cubed times,
derivative of this, keep itself.
Oh, you just keep it as is?
Yes, e to the x squared, but then what's the derivative of x squared?
2x.
2x.
So anything with an e, even though it has the x squared, it stays the same?
It's itself.
Okay.
Okay, let me try to really quickly diagram something here that I think could be helpful. So there is power rule. There is product. There is a quotient rule. Okay, and these could all lead to chain rule. Because we saw that here. We saw power rule leading to chain rule. That was this one right here. Do you see that? You do power rule first and then chain rule. Okay.
So you use chain rule when there's something like kind of like left over?
Yes.
Okay.
That's exactly what it is. Product rule can lead to chain rule. Okay, we just saw that in this example here. Product rule, because there's an inside function, and then quotient rule similarly leads to that. Okay, but what I've kind of left off is like these functions, and these functions are like sine of, e of, ln of. These all have a derivative, but then they also lead to chain rule. So,
and ln, the derivative of ln is what, 1 over x, right?
Yes, but let's say it was 1 over, x to the 10th, then it's chain rule.
And you would do chain rule. Okay.
So what I was trying to just see here is that you're either starting with power rule, a function, a product rule, or a quotient rule, but then it could lead to chain rule.
Okay.
And that is all the time that we have for today. I do see you schedule a lesson for tomorrow, so I'm looking forward to helping you then. Come with your questions and do the best to get you ready for this test.
We're going to review tomorrow in class, so I'll probably have some stuff to go over.
Excellent. Well, thanks so much for scheduling, and I'll see you tomorrow.
Thank you.
Bye now.